In continuing our intro to C, this video is a high-level introduction to C statements, variables, and how we store information into variables. Every statement in C ends in a semicolon. For those of you who have seen MATLAB, the semicolon has a very different purpose. Every statement has to have one. C also uses other punctuation symbols. Commas are used to separate lists, curly brackets surround blocks of code, and C also gives special meaning to some special symbols. In this video, we'll see the equal sign and the asterisk as the multiply operator, but there are a lot more of these. C has some words that the compiler knows about. These are called reserved words, and they're always in lowercase. Your development environment will probably color them specially. In CLion, they're orange. When we define something, we name it with a standard identifier. Some of these come from libraries like printf and scanf, and some come from things that we declare. C is specific that these identifiers contain only letters, digits, and underscores, that they cannot start with a digit, and that they cannot be one of the reserved words. As a general rule, you also shouldn't name things the same things the standard libraries give us, like printf. The naming convention for these identifiers is that they're lowercase and words are separated by underscores. So, if I want to name a variable that holds the total cost of something, I'd name it like this. One of the things we name is our variables. A variable is a place where we can store information. Every variable has three things: a unique name that follows the rules of standard identifiers we just talked about, a place in memory, and a value stored in that place in memory. C is a strongly typed language, so we have to tell the compiler about every variable we're going to use. We do that with a declaration statement that is of the form type variable name semicolon. The purpose of a declaration is to tell the compiler what kind of information the variable is going to hold, so it knows how much space to allocate. It also lets it do safety checks to be sure that we don't try to store something else into that space. For now, we'll just use the type that C gives us. Later, we'll learn to create our own. And if you want to skip ahead, check out the video above about type defs. As an example, let's look at our example code again. If you want to see a video that just covers this code in detail, click the link above. These statements declare our variables. We are using two types, int and double, to declare four variables. Int means that it will hold an integer, and double means that it will hold a real number. To see the rest of the types that C gives us, click on the link above. We use assignment statements to store information into variables. They are always of the form variable name, equals sign, expression. The right-hand side is an expression that evaluates to the value we want to store. And the left-hand side is the name of the variable where we want to store the value. Read these as variable gets the value expression. That equal sign does not imply that they are equals. It isn't a comparison. It's an action. Since variables can only hold one thing, any value that was in the variable before gets overwritten with the new value. Let's look at an example. This code first declares two variables named sum and total, and each can hold an integer. When the compiler sees that, it generates code that allocates space for them. We can mimic that with a memory diagram that shows each variable and the memory space it's given. The first assignment statement is read, sum gets the value 100. That will store the value 100 into sum, so we'll write that here. Similarly, total gets the value 32, puts a 32 here. Now this last statement is a little more interesting. It is an assignment statement, but the right-hand side encodes a calculation. The execution of an assignment statement is always evaluate the right-hand side and store it in the variable on the left-hand side. So this statement will start by evaluating sum plus total. It will go to memory and get the values stored in those variables and then add them together. So that evaluates to 132. That's what gets stored into sum, overwriting the original value of 100. Now that last statement shows why you don't want to read the equals sign as equals. If you thought of it as a comparison, your brain would break. Remember, it's an action. Evaluate the right-hand side and store the result in the variable at the left-hand side. Thanks for watching. There's more good stuff, so subscribe.